Recording start. Hello. Yeah, hello. So we'll first take some doubts, week 12 session or anything from before that you need.
Hi bro. I want to ask a question from 6 weeks.
Okay.
Can you explain how the inception block works and how it's used over other blocks? Yeah.
Okay. So I'll basically briefly cover the most important aspect, the reason why inception block itself was introduced. Okay. So if you know all the architectures till before inception, the inception block was actual part of this Google Net architecture. And so the idea was that if you wanted to, in general, whenever up till ResNet and those architectures, what people used to do is, let's say you have some input map, size m cross n, and some c in a number of channels. Okay. And you applied some kernels of size k cross k. Now, since the input channel is has some depth, the kernel itself will also be a volumetric kernel whose size also will be cm. Okay. And this entire thing will pass over the entire input, and basically you will just calculate what will the output size. Let's say the output comes out to be O cross O size, and you have, let's say, such. So in general, up till ResNet, what people use. Am I audible? So till ResNet block, what people used to do is, if you wanted to try and get different sized feature maps from the inputs, what you would do is, you will try different kernel sizes to get what can I say, a different resolution capture of the input map. Let's say you wanted to explore 3x3 kernel maps, you can, or you wanted to explore 5x5 kernel maps, and so on. So the idea of the inception block was that you can keep on trying. So let's say uh, your input was n cross n, and from that same input uh, at any particular layer of size n cross n, you wanted to have different resolution captures. So you could go for a 3 cross 3 and a 5 cross 5, and basically you will have from this 3 cross 3 you will get certain size. So let's say for the sake of this example, that you applied the appropriate padding and you ensure that the output is also n cross n. So this n cross n was uh, this was achieved with I would say resolution capture of 3 cross 3. Okay, and let's say this was another feature map that was obtained, but with the resolution capture of 5 cross 5, and then you for this also you applied the appropriate pattern to get the output map of size n cross n. Okay, so now what you would do essentially is you concatenate both of these and one behind the other, and so you'll have a bunch of, if you had a bunch of these 3 cross 3 and a bunch of 5 cross 5, so you are basically concatenating all the 3 cross 3 and all 5 cross 5 feature maps, and you are getting a different I mean basically the whole point of this is to have the various kernels, right? So you applied a 3 cross 3 resolution many number of kernels, and applied many of the 5 cross 5 resolution kernel maps also, and that got you a better representation of the input. Okay, is it making sense till this point?
Yes, sir.
Okay. So when you did this process, so when you took an n cross n feature map and you applied a 3 cross 3 kernel size, okay, so what we will do is we will take an example and see what is the amount of computation that was required for a particular case. Okay, so assume that your input is, let's say, 28 cross 28 input, and there are 192 such features. Okay, so this is your input, and let's say you applied a 3 cross 3 kernel, and you had, so this kernel will also be having a depth of 192, because that is the depth of your input, and let's say you applied such 128. Okay, so and you applied the appropriate padding so that your output is also 28 cross 28, and the depth of the output will be 120, because that is the depth of the that is the number of the kernels that you are looking for. Okay, so can you calculate the number of total operations that went on in this process? Try and calculate the number of operations that took place in this entire process. So you had a kernel of size 3 cross 3, you had an input that is given 28 cross 28 cross 192. So what is the number of operations that took place to generate you this output? And for the sake of it, let's assume that there is no bias. Okay, I mean, you can ignore the bias operations. I'll give some 5 minutes. You can try. So the key thing that you need to know here is you have ensured the size of the output to be same as the input. Okay, so the appropriate padding has been applied. Padding and the stride is fine. So maybe stride is equal to 1 and appropriate padding. You can put your answer in the chat box. Yeah. So one answer we are having is 3 cross 3 cos 20, 128. Okay. So that is not actually correct. We'll discuss the number of operations that actually take place. Okay. So you had this 28 cross 28 input. Okay. So since the appropriate padding is applied, you can imagine that for the first block, this is how the kernel will get applied on it, the 3 cross 3 kernel. Okay. So now this 3 cross 3 kernel along with the entire padding around your input. So this specific, just for the first block, the amount of operations that are taking place is actually 9. That's just 3 into 3. Okay. But this is just for the first block on the first layer. Okay. And there are such 192 layers. Okay. So just for the first block on all of these 192 layers, we are doing 3 cross 3 cross 192 operations. Okay, and all of these operations are going to happen for the entire. So while the convolution operation happens, it goes one block at a time rightwards, then to the next line, one block at a time, then to the next line, and so on. So there will be such 28 times 28 operations. Okay, and there are total such. So this was the operation of one of the kernels, which was this 3 cross 3 cross 192, and I'm telling that there are 128 such kernels. So this is multiplied by 128. Okay, so that is the total number of operations that takes place when you apply convolution operation. So this is a very huge order of operations, and you can in fact try and calculate this number. Just open your calculators and try it out. So this 3 cross 3 was for the first one kernel on one layer at one block. There are the input size is 192, so you had 3 cross 3 cross 192 for the one block. Then you had 28 cross 28 because the padding is appropriately applied, so you are going over the entire image, each block. So that 128 cross 28, and this 128 because there are 128 such kernels. Okay, so you can see. Okay, so we have one answer of what is the number of operations that has taken place, and that's about 173 million operations. Okay, so you can appreciate that this is a very huge number of operations that are taking place, right? So
Yeah.
so what we see, uh, the this is one of the problems that was what you can say discovered, and the way this GoogleNet architecture, they tried to present that it can be sorted. The solution that they presented was that instead of applying, so this is our goal. We had an input of 28 28 192. Okay, and your desired output is 28 28 120. Okay, so that is the desired mapping that you want, and you want to use a 3 cross 3 resolution kernel being applied over the entire data. Okay, so this is our target. As we saw before, directly applying this 3 cross 3 kernel of and 128 such kernels, that is creating a good number of computations. But what we are trying to now see is there a way around this thing so that we can at least reduce some of the computations. You will still have a lot of computations, but can we reduce this number in some form? Okay, so the idea that was proposed in the GoogleNet paper, or the inception block as they named it, it was that instead of applying this 3 cross 3 cross 128 kernel directly, you will first apply 28 to this input of 28 28 192. You will first apply a 1 cross 1 kernel, and let's say you choose any small number, which in this case we have chosen 96, which is just half of the this number. Okay, so the output of this is again going to be a, let's say you applied the appropriate padding and you got 28 cross 28 cross 96. Okay, but then you would say my desired output was 28 cross 28 cross 128. No? So that, then they say that you now apply the 3 cross 3 kernel that you wanted to apply and 128 such kernels, I mean 128 such kernels of 3 cross 3. So each of these will be 96 dimensional. Okay, the output of this is going to result in 28 28 120. Okay, so now I would like you guys to try out the, so the difference that we did here is we applied first a 1 cross 1 kernel and then the 3 cross 3 kernels. Okay, so this 96 is actually the number of such 1 cross 1 kernels, not the depth. Okay, so I would like you guys to try out and find the number of computations that would be required in this pathway. If you need, I will just show the previous scenario where we calculated this computations. Okay, so we had 28 28 192 input with 3 cross 3 kernel and your output was 28 28 128. The number of operations was calculated this way, but now we are first going to apply a 1 cross 1 kernel and such 96 kernels, and then you are going to apply your 3 cross 3 kernel and such 128 kernels to get your desired target. If you have the answer, you can put it in the chat. So in this case you are actually supposed to get lesser number of computations, and we will see how that works out. So what you do, a 1 cross 1 kernel, uh, the depth of this kernel is going to be 192, because that is the size of your depth of your input. Okay, so when you pass this 1 cross 1 cross 192 over the entire 28 cross 28 image, you will have 1 cross 1 cross 192, so which is essentially 192 operations. Okay, and this goes over the entire 28 cross 28 image that you had started with. Okay, and there are such 96 of them, so that is what you have. After this is done, you have to add. So once these operations are done, that is, you have obtained this output. Now you are applying the 3 cross 3 kernel whose depth is 96, and there are 128 such operations. So in that case you will have 3 cross 3 times 96, because that is the depth, times 28 cross 28, because you are maintaining the size by applying the appropriate padding, and such 128, because that is the number of kernels that you are working with. So now you can try calculating this number. That is not the answer you get actually. The answer should be somewhere in the orders of 100 million. Yeah, that looks more close. 101. Okay, so now you can see, right, the applying a direct 3 cross 3 cross 128 kernel, that was resulting in 173 million. But doing this step operation, so you first applied a 1 cross 1 kernel, and then this then your 3 cross 3 kernel, you actually managed to achieve the goal, the target that you wanted to achieve. You have achieved the same, from the same input to the same output size, and the same, in fact the information that this captures is still the same. You can check that the receptive field of this operation and the previous operation, that will turn out to be same, but you will notice that the number of operations that this process required was much less. Not too less, but still you have achieved at least a few 100 billion, no, some 70 billion, 70 million operations are less at least. And over the training process, this will amount to a good difference of speed. Okay, so that is what one of the key ideas that was proposed from the inception block. And so what they did was, whatever might be the size of your input, and you want to try out, let's say, different size features. Let's say you wanted to give 3 cross 3 a shot, 5 cross 5 a shot, and you also wanted 1 cross 1. The inception block, what it suggested was, instead of directly going for your 3 cross 3, you first use a 1 cross 1, then you use a 3 cross 3. Same for the 5 cross 5. And there is nothing to do for a 1 cross 1, so you can directly apply. And this operation, this set of operations, is far lesser than this. Okay, as we saw above. So that is one of the good things about the inception block, and I now I will now tell you to like go through the notes, the lecture on this Google Net architecture, and where the sir actually explained about the inception, one of the blocks of this architecture. So it was the inception 3A block. So you can now try to go through this calculation and try it out for that inception 3A block and see how that works. Okay, I hope that answers your question.
Yeah, thank you.
Okay. If anyone has any other questions, feel free to post in the chat. We'll take some questions till about 7, and then I'll try to discuss some aspect on the week 12's content. Okay.
Yeah, hi.
Yeah, you can post your question in the chat. Week 8 main topics. Huh? Can you please be more specific? Like what exactly would you like? If I remember, week 8 was mostly about RN and some of those things. Right? Okay, till then we will just go over the general architecture of what an RNN is about. Okay. We will explain steady diffusion equation with a feed forward neural network. Okay. Actually, my today's demo is about diffusion equation solved with a neural network. So So we'll just briefly go over the RNN architecture, and I will come to the diffusion equation with neural network. Okay. So as you know, like the main purpose of RNNs is actually to work with sequential data. Am I audible? Okay. I hope my screen is. So the main purpose of the this RNN architecture is actually to work with sequential data. So sequential data could be you have some noise or some audio signal that you are trying to process, or you could say in natural language processing that could be a bunch of words, a sentence, and this sentence has sentence is basically sequence of words. So that could be your data that you are working with. So in such cases, the architectures like CNN and they may not be very suitable. So because you want to capture the order in which the data is coming in. So that is what RNNs are used typically for. So there are multiple variants of RNN, LSTM and GRU, but I will only go over the RNN, the general architecture, and you can go and revise the appropriate part of the VK content. Okay. So the main philosophy of an RNN is essentially that, let's say you have some, so basically you have some input X, let's say. So what this network really does is it will always maintain a something called a hidden state. Okay. And so you can imagine this as some process happening on this input X1. Okay. And you can generate some Y as a prediction out of this. Okay. And what you do is, along with this, you try to this is something called the unrolling of an RNN. So what this will do is, if you have a input that is going to come later down the line, let's say from X2, which is coming the next step, you will try to get some information of some processing information from this X1, and then you will feed it to the block, and that is what you want the next step output to use. So you want the next step output, the prediction, to use the current step input as well as something from the past, some processed information from the past. Okay. I hope that is making sense. And you keep on repeating this process, so as for as many number of inputs that you are going to work with. Okay, that's the main idea of RNN. And what we essentially do is like the traditional neural network architecture. Here you work with two weight matrices, you can say. So at any time, if you want to create your y1 y hat prediction, what you will do is you are essentially applying this in fact there are three weight matrices I should call. So this one will be HU. So okay, go sequential. So the first thing we need to look at is what to do with our input x1. So this input x1, you will run it through a weight matrix, let's call it WXH, because this input, this weight matrix is going to convert X input into your hidden state. Okay. And then this hidden state is also going to get processed to be sent to the next iteration. So that weight matrix, let's call it HU or HH rather, because it has to generate another hidden state only. So this H2. Okay. So maybe I'll start naming this. X1 is going to get some weight matrix is going to get applied, WXH, on this X1 to give you some H1. This H1 is going to get applied with a weight matrix WHH to give you a next step hidden state. Okay, this H2, and the output at any time, let's say y1, it's going to use this H1 state, and that is going to get applied with the WHY. Okay. Okay, so there are three matrices that you can see. Right? There is a WXH, which converts the inputs to the hidden state. Then there is WHH, which basically you can imagine it as what should go from current hidden state to the next hidden state. Okay. And then there is another WHY, which is basically telling you what from the current hidden state you should use to generate your output. Okay. So for the sake of simplicity, from now on we will, as was done in the lectures, so WXH we are going to refer it as U, WHH we will refer it as W, and WHY we are going to refer it as V. Okay. So you can write these same expressions as y is equal to some v of h at any time. H is equal to u of x, and the next step h2, I would say, is some w times h1. Okay. So that is the general idea, and in a RNN, as you go through and keep on applying new inputs, these weight matrices themselves, they are not going to change. I mean, it's the same weight matrices that are going to be trained over the entirety of your sequence. Okay, is that part making sense? So basically, that's why they usually draw RNN as a single block, and they make it like this. Because what they are trying to represent here is that this same thing is going to work with the next x. Okay, and so essentially what you are doing is, since there are many variants of RNNs, so you could work with having multiple inputs and a single output. So x1, x2, x3, but you might be interested in only the out. So let's say you are interested in something like whether a particular, let's say you are analyzing some reviews for a particular website. Okay, so for a particular product in, let's say, Amazon, and the review has some words. Okay, and all of these words you send in one by one. You want to know whether it's a positive review or a negative review. So this y hat that you are predicting out, it might be a single number. So you want to run through the entire review and generate out the basically, when you want to understand whether that review was a good review or a bad review. Similarly, you can, instead of taking just one output, you can take the output at all the times. So this might be some translation kind of application. So you take in the words that are coming in and keep on translating them one after another. Okay, and there is another variant where you might not have any input later down the line, but you just keep on working with the hidden states themselves and try to generate a sequence. So this will be something similar to what ChatGPT kind of architectures have. So you have input coming at only, let's say, this is not what ChatGPT does, but you can have an analogy like that input comes in only at one time, but you keep on generating outputs from it based on your architecture. Okay, so based on these different architectures, you still hold this key idea that you are that is what RNNs will work with. So you will have these three weight matrices that you want to keep on training, and the loss calculation that is actually very important. Maybe we don't have time enough to go through it. You can go through the lectures and try to look at the loss, the way this loss is. So basically the gradients are calculated. So at any time you are looking at the prediction that you have made, and if you have a corresponding label of the true label or true output, you can cross you're you now need to have this loss being so the loss doesn't get applied only at a particular future time. Okay, so it's not something that uh, that will use only update only. I mean, the goal of this loss optimization, I would say, it's not just to uh, work with the last input that you got and get you the get you correct output at that point. You want the outputs at all times to be correct. So this loss has to propagate through the pack to all the inputs. All the previous inputs also need to be accounted for when you are calculating the loss. So that is one of the key concepts that you need to go through. So that is what is called back propagation through time. So this is one of the key concepts that you should study before your exams. Okay. So we'll now try to go to the diffusion equation problem. But, okay. So they are asking for steady diffusion, not unsteady, which is better. Okay. So uh, like instead of going for a 1D case, I'm directly going to jump to a 2D case. And the setup for the demo that I have today is as follows. So you have a, let's say, a plate. Okay, and for this plate, the top wall of this plate is, let's say, maintained at 100 degrees Celsius. Okay, and the side walls, they are being maintained at 0 degrees Celsius. Okay, and what you want to now find out is what is the temperature, or what is the temperature profile throughout this plate and in the steady state condition. So we are now looking at a steady version of the problem. So you are interested in knowing what should be what will be your temperature and at any random point in the domain. Okay, so there are traditional ways to handle such problems, which basically what they do is they will try to discretize this entire domain, putting some mesh kind of thing, and they will use some schemes. So before I jump into that, maybe I should tell the governing equation for such a scenario. So since this is a steady state condition, the governing equation becomes this thing. Okay, if this was not steady, there would have been a dt by t time also, but since it's steady, I'm going to put it 0. Okay, and there could be a source term also if you want, but let's assume that there is for this particular case there is no source term is being assumed. You have boundary themselves being maintained at these conditions by some source that we don't care about, but assume that these boundary conditions are being maintained somehow. Okay, so and this is the governing equation that is to be abided when you get all the temperature values for all the points inside the plate. Okay, so the traditional way for solving such a problem will involve some grids, and what you will do is you will also apply some schemes which will, such as finite difference or finite value, whichever one is your favorite. Okay, so you will basically discretize this entire thing, since the governing equation doesn't have any uh, doesn't talk about discretization. It doesn't say that uh, your domain needs to be discretized and only then you can. So the temperature, it doesn't say that the temperature inside this entire block is same. In reality, that temperature in each of the blocks, in fact throughout the blocks, is going to be different. But for our computation purposes, we need to have uh, have it written in terms of grids, or have the computation take place in terms of grids. Okay, so typical methods such as finite difference, they will calculate these temperatures at the grid points along with all of these boundary conditions. Okay, so the way they do is there are several methods to even solve such a thing, and I will not go into any of the methods per se, but just know that there are traditional methods to solve such a thing. What I will do today is I will try to explain how a neural network could be used to find the solution, and find a solution that is abiding this governing equation as well as these boundary conditions that are being specified. Okay, so any doubts at this point? Any doubts in the general setup over here? Okay, so what we are going to do with this neural network architecture in this question is that uh, so we'll let the network take in any input coordinate x comma y, which will be, so let's say we define our grid in a particular manner, that x is along this shorter edge. So one thing that I actually forgot to tell is the dimensions of this grid. So for dimension of the plate, so assume that this plate is 1 unit in this direction and 2 units along this direction. Okay, so we will work with this and we'll see how a neural network will solve such a scenario. So the goal of this neural network that we are going to work with is that it will take in an input x comma y coordinate, and there will be some hidden layers, some processing that will happen in between, and it should return out the temperature in the steady condition. It should return out what is the temperature at this particular x comma y location. So let's define x along this and y along this. So if I choose this point for my evaluation, I want to know what is the temperature at this x comma y location. There is some bunch of hidden layers and stuff. Okay. So the whole the the thing that the neural network is now going to do is, so previously what we saw, uh, it's essentially learning the solution of this system. Okay, so this neural network is now, I'll maybe call it a function f. So I'm going to represent the entire neural network as a function f. It takes in input x comma y and gives me out the predicted temperature. Okay, but the constraints that this solution has to be obtained under are these: the governing equation and the boundary conditions. Okay, so the way physics informed architecture works is that you specify the laws in terms of both the governing equation laws so the loss is put as a the governing equation. So how far are your predictions from this scenario? Okay, at any given point you need to have this thing achieved as much as you can. Okay, so governing equation loss, I'll put a L over here, as well as a boundary condition loss. Okay, so that is what the total loss is going to work with. If your problem was a unsteady problem, which means there was a time dependency also, then you might have some specified initial conditions that also you need to consider. So in that case, your loss will involve both boundary condition and initial conditions along with the governing equations. Okay, is that part making sense till now? Okay, so that's the general idea of what the loss function would be like. And there are actually a bunch of tricks and ideas that come up when you try to implement such a scenario. So I will try to go over some code and show the demo of how a physics informed neural network is actually applied. I hope my screen is visible. So yeah, so here we have a demo. So there is a I have two solutions here actually. So I've used a traditional method to solve this problem setup that I described. So the steady state temperature for this solution, for this problem, it ends up, the solution looks like something like this. So you can see the top wall was maintained at 100 degrees Celsius and the side walls were all at 0 degrees Celsius, and what the temperatures at different points are throughout the plate. Okay, so I will not go over the traditional solution in detail, but the idea here is that there is something called a point Gauss-Seidel method, and what you essentially try to do is you go over the each and every point in the domain one by one. You basically first initialize the entire thing with some random values, and you look at the points around a particular point and see the values of those points and try to update your location, update your temperature at a particular point. This process you do for all the points, and you repeat this process over many iterations. You will notice here that the iterations that this particular method took for for achieving the steady state answer. So there is always a error limit that you work with. So here we have checked that your solution is not varying beyond this point. So over the iterations you keep on finding your solution, and there comes a time when the solution is not varying much, and in this particular case we have limited the variation. So if your solutions are not varying within 0.01 of current and the previous iteration, then you would stop the process. Okay, so this particular method actually took 2315 iterations to get you to this steady state solution. And this is also important. So you have chosen 41 and 81 grids along each of the dimensions. So along this x you have chosen 41 grid points, and along y there are 81 of them. Okay, so now I will try to give some demo of how you would apply the same, how you solve the same problem with pins or physics informed neural networks. So these are just some library imports. I will come to this part a little later, but for now I have just noticed that I have set this power value to 1. Okay, and as I described, so this is just a simple feed forward neural network. We have chosen some arbitrary hidden layer units, and the main thing you need to notice here is that the size of the input is 2 and the output is 1. Okay, so the input is going to be an xy coordinate and the output is going to be a single temperature value at that particular xy coordinate, and you are going to run the entire thing through this neural network to get the temperature. Okay, so yeah, here I have defined a function for the top wall boundary condition. Okay, so we want all these points to have to be maintained at 100 degrees Celsius. So that is what we are essentially doing here. So here this x is actually a let's say the entire grid. Okay, so this x is here denoting the entire set of grid points, and what we are doing is we are essentially taking the first row of that and setting them all to 100. That's all. That is what the top wall boundary condition is actually. And the main thing that for such a application is that you define the loss function appropriately. Okay, so we'll come to the loss function. So as you know that we have set this feed forward neural network, and let's for the case we are going to call it as pin. Okay, and here also X is denoting the entire grid points. So the Y pred is going to be same size as your input X. Okay. So when you pass the entire input X through this neural network, this is going to give you temperature at all points. Okay. So maybe I will mention that also. Okay. All right. That's the grid. Okay. So this is going to be the same size as the entire grid. Okay. Then basically what we are doing here is we are computing the gradient. So I actually covered this in the previous session. This is the same thing. We are using the AutoGrad functionality of PyTorch, and what this is going to do is it's going to find the derivative of this x, y prediction, the output with respect to x. Okay, and it's doing the same thing over here also. Ideally this should have been the loss function. No, this is correct. Yeah. Because so this essentially is giving you dt by dx. And this is going to give you dt by dy. Okay. And since your governing equation was actually d square t by dx square plus d square t by dy square, so we are taking the derivative again of the entire thing. This term is actually your d square t by dx square. This is going to be your d square t by dy square, and the residual that you are computing. So this is your governing equation also. Okay. This is essentially saying that the d square t by dx square plus d square t by dy square, which is your residual, and this residual is going to be your L governing equation that I wrote when I was describing the theory. Okay, and I'm just reshaping the prediction here. So this x here, when it was passed as a list of points. Okay, but here we are reshaping it into the shape of the grid so that we can apply the boundary conditions. So what we are doing here is we are calculating the error at the top boundary. So from this reshaped y prediction, you are checking what is the first row, the entire first row, whatever are the values, they should all be 100. So that is what our top BC function actually set. All these values were 100. So you check the difference between them. That is your error. This weightage part I will come to later, but since here I had set it to 1, we'll see what is the effect of changing this weightage. Okay. In fact, for starters, let's comment this part out, and I will directly pass the top boundary condition error. Okay, this I'll pass this quantity directly without any applying any weightage. And so yeah, so this is the total boundary condition loss that we are now going to compute. The top one is the only tricky one because that was at 100. The rest of them you can directly take the square of the each of the boundary. So this is the left boundary, this is the right boundary, and this is the bottom. Okay, the bottom of the plate. Okay, so we are taking the loss at each of them and adding them up. That is your total boundary condition loss. And the residual, this is the, which is this residual that you computed over here. This is the governing equation residual. Okay, and you are taking the mean of the boundary conditions also and residual also, and that will be your total loss. Okay, and this entire thing is just actually to run the network. For the sake of this, I will keep the address as 10,000 only. And yeah, so this is the general process. So you basically set the gradients for this particular iteration to 0. You compute the loss and you compute the gradients properly, and then you optimize and update your weights of the network. And we'll print the loss at each after every 1000 epochs. So here one epoch is considering the entire plate at once. Okay, and we'll wait for some time. I think it is there 10,000 iterations. If anyone has any doubts till that point, let me know. Till this thing runs. So now you will see that the loss is actually very significant. And if you plot the temperature, yeah. So you will notice that at this corners, the what was the reason why that weighting function was actually needed was that at the corners the boundary conditions suddenly changed from 0 to 100 degrees Celsius. So this particular point, it has a very sharp derivative. So it will, on one side it's being asked to have a temperature of 0 degrees Celsius, and on the other hand it's suddenly being asked to have a temperature of 100 degrees Celsius. So at these corners the gradients are going to be very sharp. So a method such as pins will suffer in such a case. So because we are trying to find a function basically throughout this entire thing as the solution, so that function becomes very sharp at it has very sharp gradients at these corners, then it might mess up, and that's why you are seeing the loss being so high. So what we try to do in such a scenario is we try to apply something called the weighting function. So in fact since I passed the boundary condition error at the top wall directly, all the points were equally weighted, okay, at the top. But if you want, you can weigh them differently. In such a case, you could have a strategy like this, so that the points, so the index here represents the x the grid index at the top wall. Okay. So what I'm going to do is at the top wall or the top row, I'm going to weight the first index to be 0. That means I'm not expecting it to follow the 100 degree Celsius boundary condition at the corner at all. But in the middle of it, I will expect it to have complete weightage of the 100 degree Celsius boundary condition. Okay, and at the other corner also, I'm allowing it to not have any weightage of that boundary condition. So the same thing, you can try different values of power. So in this case, the gradient is, so you are having, the ideal way would have been the correct way would have been all of these having a value of 1, all the indices, but the thing is that creates the sharp gradient. So we want some way of allowing it to have a gradual change. So you can try different values of the power, and in this case even this is quite going to result in a sharp solution, but you will see that this will give the least error. Actually I had a lot of the comparison between the neural networks prediction and the traditional methods solution, and that is what you can see here. So for most of the region, the temperature is identified correctly, so the error is 0, but at these corners the method has not succeeded. Okay, but you can achieve somewhat better results, so you can note the error here. So here the error is significant, 2515. Okay, but by introducing the weighting that I just described, this parameter I will set to 0.05. We'll see how the network performs in such a case. So what I essentially did here is that I'm relaxing the top wall boundary condition slightly. Okay, it should not be called square. It should be so you will see that the solution is solved. I think the iteration should have increased, but fine. Yeah, in this case what the solution is trying to do is it's having a loose the condition is slightly relaxed at the corners. Let's see whether there is any improvement. There is no improvement. In fact, it has gotten worse. Perhaps the stronger differentiation was better. I'll try to do it for like more iterations. thing is, when you attempt to solve such a problem with the traditional method, you you are since you are solving for any particular grid, you can easily set this boundary condition of, so this there is no constraint of differentiability, or you are not concerned with uh, what are the derivatives at each of the corners. So in such a case, you will apply this sharp condition, and you will basically work with it. But when applying a method such as pins, you would like the function to be differentiable, so that the gradients don't explode. That's why we are applying this weighting, and it's true that it will actually make it worse. Okay, so the training is over. Visually, I don't think we will be able to distinguish anything. But yeah, the this is I think this is slightly better than the previous one. But yeah, you will notice that around the corners, the number of points. So the red the value, the more error it is. So the error is lower at these points. That's what this is. Okay. So I hope that helps. Okay. That is all actually for today's. But if you guys have any doubts, we can cover this. Maybe I will share the collab also. So if anyone has any doubts, we will take those, or we'll conclude the session. Okay, then if there are no doubts, let's conclude the session.